How does the tech that runs our world really work? We break it down to its fundamental truths. This is First Principles.
You're standing in a sterile white-walled room, watching through a pane of safety glass. Inside, a robotic arm, a gleaming metal limb of yellow and gray, hovers over a microchip. It descends, its metal pincer fingers closing in with impossible delicacy. It picks up a component smaller than a grain of rice, rotates, and places it onto a circuit board with a precision you couldn't hope to match with your own hand. The arm retracts, hovers, and does it again, and again, and again, flawlessly, 100 times a minute. We've all seen videos like this. We know this is how our phones, our cars, our world is built. And we tend to think of it as a simple command and control problem. A computer brain tells the arm where to go, and the arm goes. But how does this actually work? What simple, fundamental rules allow a machine made of cold steel and wires to move with such purpose and grace? Today, on First Principles, we are opening the black box of robotic motion. We're going to uncover the hidden conversation happening thousands of times a second that turns a digital thought into a physical act. The magic we see is all around us, and it's become so commonplace that it's almost invisible. Think about the last time you saw a video of one of those Boston Dynamics robots. Maybe it was Spot, the dog-like quadruped, trotting up a flight of stairs, its legs adjusting automatically to the height and depth of each step. Or perhaps it was Atlas, the humanoid robot, doing a backflip. A backflip, a feat of coordination and balance that most humans can't manage. The motion is fluid, it's adaptive, it's shockingly organic. It doesn't look like a machine executing a program. It looks like it's alive. Or consider something less flashy, but perhaps more profound. A surgical robot, like the Da Vinci system. A surgeon sits at a console miles away from the operating theater, manipulating a set of controls. In the patient, a multi-armed robot mimics the surgeon's movements, but with a crucial difference. It scales them down, filters out the natural tremor in the surgeon's hands, and performs incisions with a steadiness that is superhuman. The robot isn't making decisions, but it is translating human intent into physical action with a fidelity that changes what's possible in medicine. Even in a bustling Amazon warehouse, the magic is there. Squadrons of squat, orange robots slide underneath towering shelves of goods, lifting them and whisking them across a vast concrete floor, navigating a complex dance with hundreds of other robots without ever colliding. They move with an eerie sense of purpose. There's no hesitation, there's no fumbling, just the smooth, relentless execution of a task. The impression we get from all of this is one of supreme intelligence. We see the graceful result, the perfect weld, the stable gait, and we naturally map our own experience onto it. We assume there's a mind in the machine that understands the world in the same way we do. We think the robot's brain has a perfect three-dimensional model of its environment and is simply plotting a course through it, telling its limbs, move your elbow joint to 93.7 degrees. Now rotate your wrist by 12 degrees. We assume it's a one-way street of commands from a brilliant computer to a dumb, obedient body. And that assumption, that common misconception, is not just a little bit wrong. It's fundamentally backward. The secret to how a robot moves isn't in the command, it's in the conversation. But to understand that conversation, we have to go back to a time before it existed. A time when the dream of an automated worker was just that, a dream. The problem was not new. For centuries, inventors and engineers had been fascinated with automatons, with creating mechanical life. In the 18th century, you had marvels like Jacques de Vaucanson's digesting duck, a clockwork creation that could flap its wings, eat grain, and through some clever internal chemistry, appear to excrete it. These were astonishing pieces of craftsmanship, but they were fundamentally limited. They were mechanical puppets, executing a single, unchangeable sequence carved into their gears and cams. They were a performance, not a process. They couldn't adapt. They couldn't be reprogrammed to do something new. The real industrial need wasn't for a mechanical duck. It was for a mechanical arm. In the burgeoning factories of the 20th century, you had assembly lines powered by humans, people performing repetitive, often dangerous tasks over and over. The dream was to automate this, to create a machine that you could teach to do a job. Pick up a part, move it over here, weld it right there, and then have it repeat that job tirelessly and perfectly, forever. The first attempts to solve this problem gave us what we now call open-loop control. The name sounds technical, but the concept is incredibly simple. It's the hope for the best method of control. Imagine you're trying to toast a piece of bread. An open-loop toaster is the simplest kind. It has a timer. You put the bread in, you turn the dial to, say, 2 minutes, and a heating element turns on. After 2 minutes, a spring pops the toast up. The toaster doesn't know if your bread is thick or thin, fresh or stale, white or whole wheat. It doesn't know if it came out perfectly golden or burnt to a crisp. It executes a pre-programmed set of instructions, heat for 120 seconds, and then it stops. It has no knowledge of the result. That's an open-loop system. It sends out a command and has no way of knowing if the command was successfully or correctly executed. The loop is open because no information comes back. The first industrial robots of the 1950s and 60s, like the groundbreaking Unimate, largely worked on this principle. You would teach the robot by physically moving its arm through a sequence of points, recording the position of each joint at each point. The robot would then play back those recorded positions. It would tell the motor at the shoulder joint, run for 1.7 seconds, and the motor at the elbow joint, run for 2.3 seconds, to get from point A to point B. It was revolutionary. But it was also brittle. If a part wasn't in the exact right place, the robot arm would still go to its programmed spot, grabbing at empty air. If the arm was carrying a heavy object, its own momentum might cause it to overshoot the target. If a motor started to wear out and run a little slower, the robot's accuracy would drift. It was a system that worked only in a perfectly predictable, unchanging world. It was a clockwork duck, just on a much larger scale. To move into the real, messy, unpredictable world, the robot needed to stop just talking and start listening. So, how do you get a machine to listen to itself? How do you get it to understand its own body and its place in the world? Let's leave the factory for a moment and use a more human analogy. I want you to close your eyes. No, really. Close your eyes. Now I want you to extend your arm straight out in front of you, and then touch the tip of your nose with your index finger. You can do it, right? Effortlessly. Now, how did you do that? You didn't have a camera watching your finger. You didn't have a GPS tracker on your fingertip. You did it using a sense called proprioception. It's your brain's innate internal understanding of where your limbs are in space. It's the sense that allows you to walk without looking at your feet, or scratch an itch on your back without using a mirror. Your brain sends a command, touch nose. But it's also receiving a constant stream of information back from nerves and stretch receptors in your muscles and joints that tell it, okay, the arm is halfway there, almost there, contact. Your brain is in a constant, high-speed conversation with your body. That is a closed-loop system. This is the first principle, the absolute bedrock of all modern robotics. Motion isn't about shouting commands into the void. It's about a conversation, a continuous looping dialogue. Act, sense, compare, correct. This is the feedback loop, and it is the single most important concept we will talk about today. The robot has to send a command to its muscles to act. Then it has to have senses to perceive what actually happened. It must then compare the result with the original goal. And finally, it has to issue a new, corrected command to close the gap between where it is and where it wants to be. Act, sense, compare, correct. Over and over and over, hundreds or thousands of times a second. This loop is the secret. It's how a dumb machine can produce an action of breathtaking intelligence. So let's open the box. Let's look at the actual components that make this loop possible. First, the robot needs muscles. In the biological world, muscles work by contracting. In the world of robotics, these muscles are called actuators, and they work in a few different ways. The most common, the one that powers everything from that factory arm to the tiny motors that vibrate your phone, is the electric motor. But a simple electric motor, like one you'd find in a cheap toy, is not very useful for a robot. If you connect it to a battery, it just spins fast. It has no inherent sense of control or precision. It's an open-loop device. You can tell it to start, and you can tell it to stop, but you can't tell it, rotate exactly 47.2 degrees and hold that position. To solve this, engineers came up with two clever variations. The first is called a stepper motor. Imagine a compass needle. It always wants to point north because it's aligning with a magnetic field. Now, what if you could create a ring of electromagnets around that needle and turn them on and off in a sequence? If you turn on the magnet at the east position, the needle will snap to point east. Then turn that one off and turn on the one at southeast. The needle will jump to that new position. By energizing these magnets in a precise order, you can make the needle move in a series of discrete, predictable steps. A stepper motor is just a more sophisticated version of this. Its central shaft doesn't spin freely. It moves in tiny, precise, angular increments. If you know that each step is, say, 1.8 degrees, and you want to rotate 90 degrees, you just tell the motor's controller to send exactly 50 electrical pulses. 50 steps. It's simple, it's reliable, and it's relatively cheap. You find them in 3D printers and office scanners, where precise, repeatable movement is key. It's a step towards control, but it's still fundamentally an open-loop system. You're commanding it to take 50 steps, but you're just assuming it did. If something physically blocks the motor or it has to work against too much weight, it might miss a step, and the system has no idea. The error accumulates. For true closed-loop control, you need the king of robotic actuators, the servo motor. A servo motor is not just a motor. It is a complete system in a box. It contains a motor, yes, but it also contains a gearbox to manage speed and torque. And most importantly, it contains a sensor that is constantly reporting the motor shaft's actual position back to a built-in controller. The command you send to a servo isn't run for 2 seconds or take 50 steps. The command you send is go to position 135 degrees. The internal controller then takes over. It powers the motor to move towards 135 degrees. All the while, it's watching the sensor. The sensor might say, "We're at 90 degrees, 110, 125. As it gets close to the target, the controller starts to slow the motor down so it doesn't overshoot. If it does overshoot, say to 136 degrees, the sensor reports this, and the controller immediately reverses the motor just a tiny bit to bring it back to 135. It is a self-contained miniature feedback loop. It's like telling a friend to point their arm at a specific star in the sky. They use their muscles to move their arm, the motor, and their eyes to see where it's pointing, the sensor. They constantly compare where they are pointing to the star they want to point at, and make small corrections until they're locked on. That is a servo motor, and a complex robot is made of dozens of them, one for every joint. But sometimes electricity isn't enough. For a robot like Boston Dynamics Atlas, which weighs over 170 pounds and can jump and run and lift heavy objects, you need a different kind of muscle. You need something with immense power density, and for that, engineers turn to a much older, more primal source of power: fluid. This is the world of hydraulics and pneumatics. Pneumatics uses compressed air. Hydraulics uses a pressurized, incompressible liquid, usually oil. The principle is simple, and you've experienced it yourself. Think of a simple water pistol. You squeeze the trigger, which pushes a small piston, forcing water out of a tiny nozzle. Now imagine that on a massive scale. Instead of your hand, you have a powerful electric pump pressurizing oil to thousands of pounds per square inch. And instead of a thin stream of water, that pressurized oil is being directed into a thick steel cylinder, pushing a massive piston with unstoppable force. This is the secret to Atlas's strength. Its body is a network of high-pressure hydraulic lines and custom-designed servovalves that act like microscopic floodgates, opening and closing thousands of times a second to precisely control the flow of this powerful fluid to the pistons in its hips, knees, and ankles. It's a far more complex and messy system than clean, quiet electric motors. It can leak. It's noisy, but it provides a combination of raw power and speed that is, for now, unmatched for building robots that can dynamically move in the same way a large animal can. The actuators, whether they are electric or hydraulic, are the robot's muscles. They are what turns a signal into force. They are the act part of our loop. But acting is easy. The truly hard part, the part that separates a simple machine from an adaptive robot, is the next step: sense. A robot needs senses to close the loop. Not just senses to see the world around it with cameras and lasers, but senses to feel its own body. It needs that proprioception we talked about. And the primary sensor for this is a device called an encoder. On its surface, an encoder sounds complex, but its core principle is beautifully simple. Imagine you have a small, clear disc like a tiny CD attached to the shaft of a motor. Now, on this disc, you print a pattern of incredibly fine black lines, like the spokes of a wheel. Hundreds or even thousands of them. On one side of the disc, you place a tiny LED light. On the other side, you place a light sensor. As the motor spins, the disc spins with it. The black lines on the disc repeatedly block and unblock the beam of light. From the light sensor's perspective, it sees a series of flashes. On, off, on, off, on, off. Each flash is a pulse. The robot's controller is designed to do one thing very, very well: count those pulses. If the controller knows there are, for example, 2048 lines on that disk, then it knows that for every 2048 pulses it counts, the motor has completed one full rotation. If it counts 1024 pulses, it knows the motor has turned exactly 180 degrees. By simply counting these incredibly fast flashes of light, the robot knows the precise angular position of its joint, down to a tiny fraction of a degree. This is the robot's nerve ending. This is how the brain gets the answer to the question, where is my elbow right now? This is the sense part of our loop. So now we have the two key ingredients. We have the actuator, the muscle, that can move a joint, and we have the encoder, the nerve, that can report the joint's exact position. Now we get to the brain of the operation. This is where we compare and correct. Inside the robot's main computer, there's a piece of software called a control loop running for each joint. Let's say we want the robot's shoulder joint to move to a 90-degree angle. That 90-degree value is our goal. It's called the set point. The control loop's first job is to ask the encoder, what's our current position? The encoder reports back, let's say we're at 20 degrees. Now for the compare step. The controller performs a simple act of subtraction. The goal is 90 degrees. The current position is 20 degrees. The difference is 70 degrees. This difference, this gap between where we want to be and where we are, is the single most important piece of data in all of robotics. It is called the error. Everything a robot does is driven by the desire to make this error value 0. So, now the controller has an error value, positive 70 degrees. This moves us to the final step. Correct. The controller now needs to send a command to the shoulder motor to make it move. And here is where a layer of subtlety comes in. It could just send a full power command to the motor. But what would happen? The arm would accelerate rapidly, and by the time it reached 90 degrees, it would have so much momentum that it would fly right past it. It would overshoot the target, maybe going to 120 degrees. The control loop would run again. Set point 90, current position 120, error -30. The controller would now issue a full power command in the opposite direction. The arm would shoot back, overshoot again, to, say, 75 degrees, error positive 15, and so on. The arm would oscillate wildly around the target, vibrating like a plucked guitar string. This is not the smooth, controlled motion we're looking for. So, smart engineers developed a more elegant solution, a control algorithm that is used in almost every controlled system on the planet. From the cruise control in your car to the thermostat in your house. It's called a PID controller, which stands for proportional, integral, derivative. Those words sound intimidating, but the concepts are actually quite intuitive. The proportional part is the simplest. It says that the command you send to the motor should be proportional to the size of the error. If the error is large, like our initial 70 degrees, send a strong command. Move fast, but as the arm gets closer to the target and the error gets smaller, say only 10 degrees, send a weaker command. Start to slow down. This is like when you're driving and approaching a stop sign, you don't keep your foot mashed on the accelerator and then slam on the brakes at the last second. You start to ease off the gas as you get closer. This proportional control gets rid of a lot of the overshoot. But it's not perfect. If the arm is carrying a heavy weight, or there's friction in the joint, a small proportional command might not be enough to overcome those forces. The arm might stop just short of the target, say at 89 degrees. The error is small, 1 degree, so the proportional command is very weak. Too weak to move the arm that last little bit. This is called steady-state error. This is where the integral part comes in. The integral component is like the controller's memory. It looks at the error over time. If it sees a small but persistent error, like that 1 degree we're stuck at, it starts to accumulate it. It's like a building sense of impatience. After a few moments of seeing that stubborn 1 degree error, the integral part says, "Okay, that's enough." And it adds a little extra boost to the motor command to overcome the friction and close that final gap. It integrates the error over time to eliminate those last vestiges of imperfection. Finally, we have the derivative part. This component is all about the future. It doesn't look at the size of the error. It looks at the rate of change of the error. Is the error shrinking quickly or slowly? If it sees the arm approaching the set point at a very high speed, it predicts that it's going to overshoot. The derivative component then acts like a brake, sending an opposite command to the motor to slow it down before it overshoots. It adds damping to the system, preventing oscillations and smoothing out the motion. It's the same instinct that makes you brace for impact. You're using your prediction of future events to change your current actions. So, you have the proportional part reacting to the present error, the integral part reacting to the accumulated error of the past, and the derivative part reacting to the predicted error of the future. Together, these three simple mathematical terms, P, I, and D, form a control system of incredible power and versatility, and this entire PID calculation, reading the sensor, calculating the error, and computing a new P, I, and D command is the compare and correct part of the loop. And it doesn't happen once. It happens over and over. For a typical robot arm, this loop might run 500 or 1,000 times per second. For a highly dynamic robot like a drone or a quadruped, it might be running 10,000 times per second. It is a relentless, lightning-fast cycle of act, sense, compare, correct, that allows a robot to hold its position with rock-solid stability, or move to a new position with startling speed and precision. This is the real story. This is the first principle of motion. It's not a brilliant brain dictating a series of perfect moves. It's a collection of extremely fast, relatively dumb feedback loops, each one devoted to the simple, singular goal of making the error in one joint equal to 0. But this brings us to a deeper question. A feedback loop can explain how a single robot joint holds its position, but it doesn't explain how Atlas does a backflip. It doesn't explain how Spot can walk over uneven, rocky ground, adjusting its footing with every step. The stability and grace we see in these advanced robots seems like more than just the sum of a few dozen PID controllers. And it is, because we've only been talking about the robot's internal senses. We've talked about its proprioception. We haven't talked about its sense of balance. This is where we find the unseen giant, the principle that ties all of these individual loops together into a coherent, dynamic whole. And to find it, you don't need to look at a multi-million-dollar robot. You just need to pull out your smartphone. Tilt your phone from side to side. The screen reorients itself from portrait to landscape. Play a racing game, and you can steer the car by tilting the phone like a steering wheel. How does your phone know how it's oriented? How does it know which way is down? It knows because deep inside it, there is a tiny microscopic silicon chip called an inertial measurement unit, or IMU. An IMU is a marvel of microengineering. It usually contains two different types of sensors. The first is an accelerometer. An accelerometer, as the name implies, measures acceleration. It works on a simple principle. Imagine a tiny weight suspended on a tiny spring inside a box. If you suddenly accelerate the box forward, the weight, due to its inertia, will lag behind for a moment, stretching the spring. By measuring how much the spring stretches, you can calculate the acceleration. A modern MEMS accelerometer does this on a microscopic scale with silicon structures, but the principle is the same. What's fascinating about an accelerometer is that it's always working, even when your phone is sitting perfectly still on a table. It's still measuring an acceleration of 9.8 meters per second squared, straight up. Why? Because it's measuring the force of gravity. The table is pushing up on the phone to prevent it from falling, and the accelerometer feels that push as a constant upward acceleration. By measuring the direction of this constant gravitational pull, the IMU always knows which way is down. The second sensor in an IMU is a gyroscope. A gyroscope measures angular velocity, or the speed of rotation. A classic mechanical gyroscope is a heavy spinning wheel that wants to resist any change in its orientation. A modern microscopic gyroscope on a chip works by vibrating a tiny piece of silicon and measuring how those vibrations are distorted by the Coriolis effect when the chip is rotated. It's incredibly clever. So, the accelerometer tells the system which way is down, and the gyroscope tells it how fast it's rotating around any axis. By combining the data from these two sensors, a process called sensor fusion, the robot's brain can build an extremely accurate real-time picture of its own orientation in three-dimensional space. It's the robot's inner ear. It is the source of its sense of balance. And this is the aha moment. This is the unseen giant. A robot like Spot isn't just running feedback loops on its joint positions. It's running a higher level, much more important feedback loop on its own balance. The robot's main computer has a set point not just for its legs, but for its entire body. The set point is stay upright. The IMU is the sensor for this loop. It's constantly reporting the body's current tilt and rotation. That's the sense part. The controller then compares the actual orientation to the desired orientation, perfectly level, and calculates an error. And now for the correct part. How does a robot correct its balance? The same way you do. By moving its feet. If you're standing on a bus and it suddenly lurches forward, you instinctively take a small step back or shift your weight to stay upright. You are moving your base of support to keep your center of gravity above it. This is exactly what the robot is doing. The output of the balance control loop isn't a command to a single motor. It's a command to a lower-level motion planner that says, we are falling to the left. Adjust the target positions for all 12 leg joints to take a small step to the left. Right now, the individual PID controllers at each joint are still just trying to zero out the error between their current position and their target position. But that target position is no longer fixed. It's being updated hundreds of times a second by the master balance controller. This is the real dance of robotics. It's a hierarchy of feedback loops. At the bottom, you have the fast dumb loops for each motor. Above them, you have a more sophisticated loop managing the body's balance. And above that, you might have another loop for navigation, using a camera to adjust the robot's overall path. So when you see Spot walking over rubble, the magic isn't that its brain has perfectly precalculated every single foot placement. That would be impossible. The magic is that the robot is, in a sense, constantly falling, and hundreds of times per second, its IMU senses this fall, and the balance controller calculates the precise, tiny corrective step required to catch itself. Walking for a robot is not an act of moving forward. It is an act of continuously catching oneself from a fall, over and over. It's a high-speed, dynamic balancing act, orchestrated by the silent, relentless conversation between the IMU and the joint controllers. It's not thinking, it's reacting. It's a reflex, executed with a speed and precision that makes our own seem clumsy by comparison. So we have journeyed from the seemingly magical fluid motion of a modern robot back to its first principles. We saw that the elegant dance isn't the product of a single brilliant choreographer in a central brain. Instead, it emerges from a much simpler, more fundamental reality. It emerges from a constant looping conversation. Act, sense, compare, correct. We discovered that the robot's muscles are its actuators, powerful motors and hydraulic pistons that provide the force. We learned that its nerves are its encoders and IMUs, the humble sensors that allow the machine to feel its own body and its place in the world. And we found that its reflexes are the PID control loops, the simple algorithms that work relentlessly to close the gap between where the robot is and where it wants to be. Understanding this matters. It demystifies the machine. When we look at a robot doing a backflip, our instinct is to anthropomorphize, to assign it intent or intelligence or even consciousness. But the reality is both less magical and, in a way, more profound. The robot isn't thinking about the backflip. It is executing a desired trajectory, while a high-level feedback loop, using the robot's inner ear, makes thousands of tiny corrections per second to its joints to maintain balance. The apparent intelligence is an emergent property of many simple, fast, dumb systems working in concert. It teaches us a crucial lesson about complexity. Often, the most sophisticated and impressive behaviors we see in technology, and even in nature, are not born from impossibly complex top-down designs. They are built from the bottom up, on a foundation of simple, robust, repeatable rules. The next time you see a machine move with a speed or grace that seems to defy its mechanical nature, remember the loop. Remember the silent, high-speed conversation happening beneath the surface. It is the steady hum of a motor receiving a command, an encoder counting pulses of light, and a processor calculating an error. It is the simple, powerful, and relentless pursuit of zero.
You've been listening to First Principles. Until next time, stay curious.